Hey guys, my name is IBM, and today I'm taking you through the last lesson of kinematics. I think this is going to be projectiles entirely. Lesson 4 of kinematics is most likely going to be only projectiles. Don't forget, this is the Cambridge International Education Curriculum, and this is going to be AS Physics 9702. It's mostly question paper 1 and paper 2. Of course, some concepts here may be necessary for uh, maybe practicals, paper 3, but mostly we expect that most of the things we're discussing here are going to help us to pass paper 1 and paper 2. Here is the course outline. Do not forget the course outline. We have physical quantities and units is supposed to be the first topic in AS Physics. We have errors and uncertainties. We have treatment of uncertainties. All those lie in topic 1. Then we are currently dealing with the kinematics. We have already done dynamics. We have done force, density, and pressure. We have done work, energy, and power. We have done deformation of solids. We shall do waves and superposition. We shall do electricity, but we have already done particle physics. These are the units that we expect, or the topics we expect to cover in AS Physics. And once you master all these topics, then you are good enough to go. Currently, we are dealing with kinematics, and in lesson 4, I expect that we shall be dealing with the projectiles. So let's go to projectiles. So this is lesson 4, I think. This is going to be lesson 4. Having seen in lesson 1, we saw describing motion using words: speed, velocity, acceleration, distance, and displacement. In lesson 2, we described the motion using graphs, that is velocity time graph, distance time graph, displacement time graph, acceleration time graph, speed time graph, velocity time graph, etc. In lesson 3, we saw uniformly accelerated motion, which was including equations of motion, or equations of uniformly accelerated motion, or the equations of kinematics. And in lesson 4, I want us to concentrate on projectile motion. Motion in either one or motion in 2 dimensions. That is what we call projectile motion. Of course, in projectile motion, we are always going to assume that the motion is uniformly accelerated. So in most cases, we shall assume that the acceleration is constant. And if the acceleration is constant, we shall always assume that the equations of motion can therefore be used with the projectiles. Okay, so let us start with the simplest mode of the simplest motion, which is going to be a motion in 1 dimension, that is vertically upwards. So consider a stone thrown vertically upwards. I have an animation on the right hand side here. I don't know whether it is your right hand side still on your computer. So consider a situation where an object or a stone is thrown vertically upwards with an initial velocity. So here this animation is showing that the stone is thrown vertically upwards from this position here. So the stone moves to that position in that direction upwards, and then it returns vertically downwards along the same path. It returns vertically downwards along the same path. So to understand projectiles, we are going to first consider a motion in 1 dimension, that is vertically upwards. Motion in 1 dimension, that is vertically upwards. So if we consider the stone thrown vertically upwards, let's say with an initial speed of 20 meters per second, of course, an object cannot move vertically upwards if it's not given an initial speed. It must be projected. But I want you not to forget that if we ignore air resistance, the acceleration is constant, and in most cases, the acceleration will be equal to g. If the object is thrown vertically upwards against gravity, the acceleration will always be negative g, which is going to be negative 9.81, even if it goes and comes back. So it is important to use a consistent sign convention here. We normally take upwards as positive and downwards as negative. That is, if I'm considering velocity and displacement, but the acceleration is always going to be downward. So the stone's initial velocity is going to be positive if it is moving upwards. However, the acceleration is going to be negative because the motion of the body is always against. The motion of the object is always against the force which is acting on the object. So the motion of the object is against the gravity in this case. So the sign convention here is going to be very important. So we shall be solving problems using the equations of motion if we assume that the acceleration is uniform. However, I want you to note, as long as the initial direction is against gravity, the acceleration will be negative because the acceleration always points in the direction of the force acting on a body. For an object in space, the force acting on it is the force due to gravity, which is always acting downwards. So we shall handle several questions which include, for example, questions like how high does the object go? How high does the object go? Remember, when it reaches the highest point before it returns, the velocity at the highest point here should first become zero before it changes direction. So how high does the object rise? How high will the stone rise above the ground level if the object is thrown from the ground level? Or how high does the object rise from the point of projection? So let's consider this diagram where the stone is thrown by a person who is at a certain height above, say, the ground level and throwing the stone vertically upwards. So the first question is how high does the stone, how high will the stone rise above the ground or above the ground level of the cliff? So this person is on the cliff and we want how high the stone raises above the ground level of the cliff, assuming that this is the ground level of the cliff. So how high does the stone raise? So as the stone raises upwards, it moves more and more slowly. In other words, it decelerates. So as the stone goes against gravity, it moves more and more slowly. So we say it decelerates. It slows down in that case. So if it slows down, then how high does it go? So at the highest point, I don't have enough space here, but I'll try to utilize this page. At the highest point here, the velocity becomes zero before it starts coming back. So at the highest point of the object's motion, the velocity becomes zero momentarily before the object moves backwards. Because initially, since it was moving against gravity, it was slowing down. It was decelerating. So it means at the highest point, the velocity has decreased to zero. So at the highest point, the velocity is zero. But remember, our initial velocity was 20 in this case. So the acceleration is negative 9.81. The initial velocity is 20. At the highest point here, the velocity is equal to zero. So let's see how far it has moved from the point of projection. How far it has moved from this point of projection to the highest point. So using equations of motion, we could use equations of motion such as v squared equals to u squared plus 2as. So I think maybe I should use this space here so that I use this page effectively. So v squared equals to u squared plus 2as. Remember, we are finding the highest point has reached from the point of projection. So it means v squared is going to be 0 squared because at the highest point the velocity is 0. This should be equal to the initial velocity, which was 20 squared, plus 2 times the acceleration, which is going to be negative 9.81, then times s, where s is the distance it moves from the point of projection to the highest point. So this means s is going to be equal to 20 squared, which is 400, divide by, because I collect like terms, this plus 2 times negative 9.81 times s, it becomes minus 2 times 9.81 s. So making s the subject, I think 2 times 9.81 is the same as 19.62. So when I press my calculator, so 400 divided by 19.62. So this is 20.4 meters. So from the point of projection to the highest point is 20.4 meters. So how high does it raise? How high will the stone raise above the ground level of the cliff? So assuming it is projected from the ground level of the cliff, then the stone must raise 20 meters upwards before it starts falling again. So how high does it raise from the ground level of the cliff? So if we assume it has been projected from the ground level of the cliff, then it should raise 20 meters to the highest point before it returns. But of course, it could be projected from a certain height, which I may not want to consider at this point. Let us assume the person projecting the stone upwards projected it from the ground level of the cliff. So if it is projected from the ground level of the cliff with a speed of 20 meters per second, then it has moved through a vertical distance of 20 meters to reach the highest point. So that's number one. So we have seen how high it raises. In the vertical, remember the takeaways here are at the highest point velocity is 0, number one. Number two, the second takeaway is that as the object moves against gravity, the acceleration is negative 9.81. Assuming air resistance is negligible, the equations of motion can apply. So that's why we have used v squared equals to u squared plus 2as. Number two, how long? We shall answer questions of how long. For example, how long will it take from leaving your hand for the stone to fall back to your hand? It is leaving your hand and it is coming back to your hand. So that means the displacement is actually 0, because if it leaves your hand to the highest point and comes back to your hand, maybe displacement upwards is positive s, displacement downwards is negative s if it comes back to the same level. So that means total displacement is going to be 0 in that case. So if it travels one distance in one direction and moves back, or it falls back in the opposite direction, then it means total displacement is going to be 0. So when the stone returns to the point from which it was thrown, or if it returns to the same level from which it was thrown, it means its displacement is 0. So in this case, we are saying displacement s is going to be 0. The acceleration has remained the same, negative 9.81, because its initial direction was vertically upwards. So we want to find how long, that is time. So we can use any equation of motion. For example, we can use s equals to ut plus a half at squared to find the value of t. So since we know that the displacement is 0, I will simply say that is 0 equals to the initial velocity, which is 20 times t. Then it was moving against gravity, so the plus, we have now a minus because g is negative, minus 9.81 t squared divided by 2. So when you solve this equation, you'll have that, we shall have that 9.81 t squared divided by 2 is equal to 20 times t. So 1 t cancels with the square, and that means t is going to be 40 divided by 9.81. And I can check my calculator. 40, I think this is approximately 4. 40 divided by 9.81. So this is approximately 4.1. So the time here is approximately 4.1 seconds. So that is the time it is going to take to go and come back. And by the way, there is another equation that we would use to find the same value of time. Which equation is that? I could still use v equals to u plus at to get the time to reach the highest point. And then I will multiply this time by 2 because it travels the same distance upwards as the same distance downwards. As the velocity decreases when it is going upwards, it increases at the same rate when it is coming downwards. So at the highest point, v is 0, initial velocity is 20 minus 9.81 times t, which t is going to be equal to, I'll just say 20 divided by 9.81, which is 2.8. about 2.04. Then I multiply this by 2. So total time to go and come back is going to be twice t, which is 2.04 times 2, which is going to be 4.08, which is approximately 4.1 seconds. It is going to give us the same thing. Suppose it continues further, and if it falls below the point of projection, then we may want to know how further, or falling further. The height of the cliff is say 25 meters. How long will it take the stone to reach the foot of the cliff? So the foot of the cliff is this bottom here. So we want the time it will take to leave the point of projection, going to the maximum point and comes back to the bottom of the cliff. And I've said the top of the cliff is at a distance of 25 meters. The height of the cliff is 25 meters. How long will it take to take the stone to reach the foot of the cliff? So our task is to find the total time for all the journey, for the whole journey. Now, if you look at this demonstration here, if the object moves upwards, let's say from this level it goes up, then it comes back to the same level, the displacement is 0. But if it falls further below the point of projection, then this is going to be the resultant displacement, but of course to be in the opposite direction. So if we say initial motion is upwards, so it means displacement upwards is positive. Displacement downwards is negative. So it continues in the negative direction, a distance of 25 meters. So it means the resultant displacement is going to be negative 25, because if this was positive 20 meters upwards, and this was negative 20 meters up downwards, then this is negative 25 because it is moving downwards. So it means the negative 20 meters cancels out with the positive 20 meters, and you remain with the negative 25 meters until it reaches the foot or the bottom of the cliff. Therefore, it means the displacement is negative 25. So if I use S equals to UT plus a half AT squared, S is going to be negative 25 equals to the initial velocity was 20. So I could say this is going to be equal to 20 times t, which t we want to find. Then minus, of course, because it was initially moving upwards, so it is going to be minus a half times 9.81, then times t squared. Now, if you're a good mathematician, you can solve this equation very easily. Or if you have a scientific calculator, you can rearrange this equation and put it in the calculator, because solving this equation will not carry any mark. Solving this equation would not carry any mark. However, I can just try to rearrange it for you. So when I rearrange, multiply everything by 2, collecting like terms, I have that 9.81 t squared. I've taken it onto the left-hand side. Then minus 20t, I've taken 20t. So 20t becomes 40, multiplying everything by 2. It becomes 40t, then plus. Sorry, this should still be minus because it is already on the left-hand side. I'm taking everything on the left-hand side. So it remains minus 50 should be equal to 0. So you can solve this equation using your calculator, and you can easily find the value of t. Alternatively, you could consider the body when it is just starting to fall from the highest point. If you consider the body when it is just starting to fall from the highest point, so here we said it took 4.1 seconds. So I'm going to delete this so that I create some space here. I'm going to consider the body when it is just starting to fall from the highest point. So if I consider the body when it is just falling from the highest point, it means its initial velocity is 0. Its initial velocity from the highest point is 0. So if I use S equals to UT plus half at squared. From the highest point, it is just starting from the highest point falling backwards, so I will take u as 0. It is starting from the highest point falling backwards. It starts from 0 before it accelerates. So if I consider it from the highest point, then I will take a g acceleration to be positive, because I'm only considering motion when it is starting from the highest point falling downwards. So I'll take acceleration as positive 9.81 in that case. So I'm getting only the vertical distance, or the vertical distance from the highest point to the bottom. So this distance is going to be, already we have said it was 20 plus 25. This is going to be equal to initial velocity is 0, so this becomes a half times 9.81, then times t squared. So the displacement from the highest point to the bottom is 20 plus 5, because from the highest point to the top of the cliff was 20 as we calculated before. Then from the cliff to the bottom of the foot of the cliff was 25, so the total is 45. So here it means t is going to be, I'll find the square root, so I'll say 25 plus 20 times 2 divided by 9.81. Then I find the square root of the answer. So t is going to be 3.02 or 03 seconds. That is the time from the highest point to the bottom of the cliff. So if I want the total time, I'll add the time to reach the highest point. The time to reach the highest point was it wasn't 4.1. The time to reach the highest point was what was the time? The time just to reach the highest point, I think I deleted it here. Okay, I can still calculate it. The time to reach the highest point alone was v equals u plus at, where v was 0, so u is 20 divided by 9.81. So it was 2.0. The time to reach the highest point from where it is thrown to the highest point, the time there was 2.04. Now the time from the highest point to the bottom of the cliff is 3.0, so the total time is going to be 2.04 plus 3.03, which gives us 5.07, or approximately 5.1. Approximately 5.1 seconds. So that is the total time. So I expect that when you solve this equation here, you should be getting an answer which is approximately that. I can try to check and see if it is very close. It could give me approximately 0. So I have 9.81 times, I'm substituting t as 5.1 squared. Then I minus 40 times 5. Minus 40 times 5.1. Then minus 50. So it is approximately equal. So it is approximately 5.0 or approximately 5.1. So t, the time to go to the highest point and back to the bottom of the cliff, is approximately 5.0. So you can try to solve this. I said you can use this equation of motion. You rearrange and then you press your calculator. You put it in your calculator, your scientific calculator, to solve such an equation with order 2. The highest order is 2. You just put the equation in the calculator. The calculator will solve that. Or you consider the motion to the highest point. You find the time to reach the highest point, which we got as 2.04. Instead of multiplying it by 2, because multiplying it by 2 means going and coming back to the same level, you now consider the motion independently from the highest point falling to the ground. It starts from 0, that's why u was 0. Because it is falling downwards, independent of the initial motion, so it means action will be considered to be positive in this case. Whenever I consider individual motion starting from the highest point falling downwards, then action should be taken to be positive. The displacement will also be positive because I'm considering independent motion from the highest point going downwards. I'm not considering the whole motion going up and back. That's why I considered u to be 0, that is starting from the highest point, and acceleration to be positive 9.81. So that gives me the time from the highest point to the bottom of the cliff as 3.03. Then I added the time to reach the highest point and I got 5.1 or 5.07. Okay. Example, a student flips a coin into the air. A student flips the coin into the air. Its initial velocity is 80 meters per second. So initial velocity is 80 meters per second. Ignoring air resistance, calculate the maximum height h the coin reaches. So let's say the coin moves from the initial position to the highest point. At the highest point, remember, the velocity there is 0. So let's say it starts from this point with a speed of 8 meters per second upwards. If we ignore air resistance, then we are going to assume that the acceleration is constant. So we have equations to choose from. We know final velocity as 0, we know the initial velocity, we want to find s, we know the acceleration as negative. The acceleration going upwards is negative 9.81. At the highest point, v is 0, so I'll use v squared. For part A, I'll use v squared equals to u squared plus 2as. So v squared, the highest point velocity is 0, initial velocity is 8 squared, plus will become negative because of the minus g, 2 times 9.81, then times s. So we want s is the height h, so s is going to be 8 squared divided by 2 times 9.81. So h is the same as s, which is simply going to be 8 squared divided by 2 times 9.81. So h is going to be 3.26 meters. Then the velocity of the coin on returning to his hand, of course that one I don't even need to calculate. Because the acceleration is uniform, it means when the object is moving upwards, the velocity is decreasing by 9.81 meters per second every second. So it means now when it is falling downwards, the opposite must be happening. This time, the velocity must be increasing by 9.81 meters per second every second. So if it stops at the same level, the velocity will be the same. So that means this is simply going to be it is going to be 8 meters per second. The acceleration is the same going up and coming down. If the coin is going up, it is accelerating from it is decelerating from 8 to 0 meters per second on its way up. If it is now coming back downwards, it is accelerating from 0 from the highest point and to reach 80 meters per second at the same level as it was projected. So the motion is said to be symmetrical. So the velocity on returning to his hand is going to be 80 meters per second. If you cannot agree to that, we can check this by calculation. So by calculation, I can consider motion starting from the highest point. So if I start from the highest point falling downwards independently, it means the initial velocity is going to be 0 from the highest point. And of course, the acceleration is now going to be positive because I'm considering motion downwards to be independent of the motion going upwards. So in that case, therefore, I can still use v squared equals to u squared plus 2as. I can use v squared equals to u squared plus 2as because I don't have the time. But of course, the distance to cover when falling downwards is 3.26. So it means v squared is going to be 0 squared plus 2 times 9.81. And remember, s was 8 squared over 2 times 9.81. 8 squared divided by 2 times 9.81. This was s. And you notice that this cancels with that, so you remain with 8 squared. So v is going to be equal to 8 meters. Alternatively, you can find the time to reach the highest point and then use v equals to u plus at. Of course, the time to reach the highest point is going to be the time it will take to come back to the same point of projection or to the hand. However, to simplify this, whenever the object is projected vertically upwards, the speed decreases by 9.81 meters per second every second. If it is falling downwards, then the speed increases by 9.81 meters per second every second. Therefore, if it falls to the same level where it started from, it means it falls at that level with the same speed it was projected upwards. As simple as that. Then the time the coin is in the air, so we are taking the time it goes and it comes back. So I can find the time it goes upwards first from v equals to u plus at, then I can multiply this by 2. So this could mean at the highest point, remember velocity is 0. Initial velocity was 8 minus 9.81 times t, which gives us the value of t as 8 divided by 9.1. 8 divided by 9.81, this is 0.82. So this was going upwards. So total time is going to be twice of t, which would be, I think this is 1.64 seconds. Alternatively, I could use s equals to ut plus a half at squared. S equals ut plus a half at squared. S in this case would be 0 if it goes and comes back. Initial velocity is 8 and the time is not known. I'll just quote capital T. It initially went up, so this becomes minus a half times 9.81 then times t squared. So we correct like terms, we have 9.81 t squared divided by 2 is equal to 8 times 2 times t. So this t cancels. And you notice that t is going to be 2 times 8 divided by 9.81. And I'm very certain that this is going to be 1.62. I mean 1.64 seconds. Okay. So that is motion in one dimension or motion in just the vertical plane. But that's not the gist of this unit. The gist of this unit is going to be now motion in more than one dimension. So let's talk about motion in more than one dimension, that is motion in two dimensions. This is what we are actually going to understand as a projectile motion. Motion in more than one dimension. So we have dealt with the motion along a straight line, that is in one dimension or one-dimensional motion. So let's now take a look at the motion of particles moving in two dimensions. The ideas of vectors learned earlier on will be employed in this unit and they will be very important. In particular, we shall consider a particle moving in a plane under the action of a constant force. Under the action of a constant force. An example is the motion of a ball thrown at any angle to the vertical or an electron moving at any angle to the electric field, which electric field you will see in A-level paper 4. In the case of the ball, the constant force acting on the ball is going to be its weight. And for the electron I've just talked about, the constant force that will be acting is provided by the electric field. So, we shall be considering particles moving in a plane under the action of a constant force, which in most cases, when we talk about projectiles, it will always be gravity. The constant force will be gravity or the weight of the particle. The weight of the particle is going to be the constant force. And if the force acting is constant and is the only force acting on the particle, then the particle is going to be considered to be a projectile. So a projectile is going to be any object acted upon only by the force of gravity if we are talking about the earth. So it is going to be a projectile because the only force we shall always be considering in everyday spoken language will be the force due to gravity. In this case, we shall always assume that air resistance is negligible. And then we shall see that projectiles follow what we shall call a parabolic path. And three key principles apply or will apply to all these projectiles. The first one is on the acceleration. For a projectile or for a particle moving in two dimensions, the acceleration of the object is always equal to g. And this acceleration is going to always act downwards because the only force acting is the force due to gravity, and the gravity which is acting on the body is acting downwards. What is therefore this implying? The acceleration on the body only affects the vertical motion of the object. Because the force is acting only in the vertical, the acceleration is in the vertical because the force is in the vertical. That means motion in the horizontal is not affected by this acceleration because if there is no air resistance, then the acceleration is not affected because there is no any other force acting on the body in the horizontal. But remember, the body is going to be projected at an angle. In other words, it is moving in two dimensions. So it means in the horizontal, its motion is not affected. In the vertical, the motion is affected because there is a force acting on the body in the vertical, which force causes an acceleration in the vertical. So we shall simply say that the horizontal velocity of the object will always be constant because the acceleration of the body does not have a horizontal component. The acceleration of the body does not have a horizontal component because the force only acts in the vertical. The acceleration only acts in the vertical. And therefore, we could say the motion is in the horizontal and the vertical directions are going to be independent of each other. This is what we are going to consider as projectile motion. These three important concepts are going to be very important. We shall consider the vertical and the horizontal directions independent of each other. That's number one. Number two, the velocity in the horizontal is not going to be affected. The reason being that the acceleration of the object does not have a horizontal component. There is no force acting on the body in the horizontal. The only force acting on the body was in the vertical. The acceleration is going to be equal to g, or acceleration due to gravity, 9.81 if air resistance is negligible. And because gravity acts vertically downwards, the acceleration is vertically downwards, so the acceleration is only going to affect the motion of the particle in the vertical rather than in the horizontal. So these are going to be very important when we are considering motion in two dimensions. Okay, so a few things we need to note from what I've just said. A projectile follows a path, which we shall call a trajectory, or it follows a parabolic path, which we shall later on call a trajectory, even though we don't need to define a trajectory. So projectile follows a parabolic path with a uniform velocity in one direction, which is actually going to be the horizontal, and a constant acceleration in the perpendicular direction. So in the vertical, we have a constant acceleration, which is g. In the horizontal, we have a horizontal constant velocity. So in the horizontal, acceleration is 0. In the vertical, acceleration is equal to 9.81. So since there is no acceleration in the horizontal, because there is no force in the horizontal, then it means the speed in the horizontal should be constant or uniform. So a projectile is actually one kind of motion where the body has uniform velocity in one direction and constant acceleration in a perpendicular direction. And the path it follows is going to be called a trajectory. So every time someone talks about a trajectory, it means it's referring to the path followed by the object whose motion is only affected by one force, which is perpendicular. One force which acts perpendicular to the uniform velocity, or one force which only affects the motion of the particle in one direction or in one dimension. So the force acts in one direction, and yet the particle was projected in two dimensions. So it means in one plane, its motion is not affected, but in another perpendicular plane, its motion is affected because there is an acceleration in that plane. Some of the examples of everyday projectiles or application of projectiles in everyday life: when you are throwing a ball, maybe basketball, you are trying to aim at the net or at the basket, a bullet fired from the gun, water coming from the hose, an arrow shot from a bow. Those are projectiles. Fountains, you might have seen all these in our everyday life. They are actually projectiles. Motion, or the path followed is parabolic. The path followed is parabolic with uniform velocity in one direction and constant acceleration in a perpendicular direction. That is what we call a projectile. Okay, so we are going to start with projectiles where the body is projected only horizontally. For example, during shooting, a bullet being fired to a person who is at a certain distance away, or you have seen me throwing darts, trying to aim at the target, or throwing arrows, trying to aim at the target. You could do this initially horizontally. So let's consider horizontal projection first. So consider a particle thrown from a certain height h, but initially it is thrown horizontally. So consider the motion of two balls. One is going to fall vertically downwards up to this point here, and one is going to be projected horizontally so that it falls at this point here. So consider the motion of two balls, one falling vertically downwards and the other projected horizontally from a height h. Number one, remember, the only force acting here is the force due to gravity. So it means they both experience the same downward force, which is going to be the force due to gravity. Because the body which was projected horizontally, it was left to move under the influence of gravity, which gravity is acting vertically downward. So both of them are going to experience the same acceleration, which is 9.81. So because both experience the same acceleration, if the two balls have the same mass and they're experiencing the same acceleration, after all, even the acceleration does not depend on the mass. So both the balls will acquire the same vertical velocity. They will acquire the same vertical velocity. Thus, they will be at the same level at any time you look at them. They will always be at the same level in the vertical. And therefore, they will reach the ground at the same time. One was released vertically downwards, another one was projected horizontally. If they are projected at the same time, they will arrive at the ground at the same time. Why? They have the same acceleration in the vertical. If they have the same acceleration in the vertical and this acceleration does not affect the motion in the horizontal, then it means these two are going to arrive at the same time. So their acceleration is the same, that is 9.81 meters per second squared. And both balls will acquire the same vertical velocity because v in the vertical, we always use y for the vertical, is going to be initial velocity in the vertical plus acceleration times t in the vertical. Initial velocity for the one which was dropped vertically, initial velocity is 0. So the velocity in the vertical for that one is going to be acceleration times t. Of course, they will take the same time to arrive at the ground. If you consider the one in the horizontal still, for it was given an initial velocity in the horizontal, but it has no acceleration in the vertical. I mean the horizontal. However, because it was given an initial velocity in the horizontal, the initial velocity in the vertical is also still 0, because initially it was projected horizontally. So in both cases, this is still 0 in the vertical. So in both cases, v in the vertical is only going to be equal to ay times t. So both balls will acquire the same vertical velocity, thus they will be at the same level at any instant and hence will reach the ground at the same time. Okay, so if air resistance is negligible, so if you try to ignore air resistance, then do not forget that we can use the equations of motion that we call the Suvart equations are going to be used for that kind of motion, as we shall see in examples. So if we ignore air resistance, then do not forget that the equations of motion can apply for such motion where the acceleration is zero in the horizontal. So the Shubert equations, that is V equals U plus AT, V squared equals U squared plus 2AS, S equals UT plus half AT squared, they will all apply for such kind of motion. Now let's focus now on the diagram. For the object which is released vertical downwards, initially velocity is zero. The length of the arrow is showing the increase in velocity. So the velocity goes on increasing because there's an acceleration until it reaches the ground. So it hits the ground with the maximum velocity. Consider also an object which was projected horizontally with an initial velocity u. I want you to focus on the horizontal arrow for u. In all cases, you notice that the length of this arrow has not changed in the horizontal. What does that mean? The velocity in the horizontal remains the same as u throughout the motion because the acceleration in the horizontal is going to be zero. Whenever I put a subscript x, I mean acceleration, I mean that quantity in the horizontal. When I put subscript y, I mean the quantity in the vertical. Consider the same object which was projected horizontally. Initially, there was no arrow in the vertical for that object, but then the arrow starts growing in the vertical, which means it's only the velocity in the vertical which goes on increasing because there is an acceleration in the vertical. Then the resultant of these two is the resultant velocity with which the object arrives at the ground. And that resultant can be got from Pythagoras theorem, square root of Vx squared plus Vy squared, as we shall see in the examples. The resultant of the horizontal and the vertical component is going to be the velocity with which they arrive at the ground, as we are going to see. Okay, so let's explore more about horizontal projection. Okay, so we are still considering horizontal projection. Let's look at this animation here. So if you consider the animation, it shows you that when the body is projected, when you look at the length of the arrow in the horizontal, it remains constant, but the arrow in the vertical goes on increasing. What is the implication of this? This animation is actually showing you that the velocity in the horizontal does not change, but the velocity in the vertical goes on increasing. That's what this animation is representing. So recall that the horizontal velocity of a projectile is not affected by the vertical motion. We said uniformly accelerated motion, there's a uniform velocity in the horizontal and a uniform acceleration in a perpendicular direction. So there will be uniform acceleration in the vertical because the only force acting is in the vertical. So this is what we mean by horizontal projection. You initially notice that there is no arrow in the vertical during the point of projection, which means if a body is projected horizontally, it means initial velocity in the vertical is zero in the horizontal. I'll always use u for initial velocity. If a body is projected horizontally, initial velocity in the vertical is zero. The acceleration in the vertical is constant at 9.81 meters per second squared. But the acceleration in the horizontal is zero. That's why the arrow in the horizontal is remaining the same in length throughout the motion. Yet the arrow in the vertical is increasing in length, indicating an increase in the velocity as the body falls. The reason as why the velocity is increasing in the vertical is because there is an acceleration in the vertical, because there is a force in the vertical, which is the force due to gravity. So the horizontal velocity remains constant throughout the motion, as we have seen in this diagram. But of course, the vertical and the horizontal motions of the body are going to be independent. So so they can be written, or we can write them independently, or we can handle them independently. And of course, we can always be able to show that the vertical height through which the object has fallen, this vertical distance VH, the vertical height H, we can show that the vertical height H from S equals to UT plus a half AT squared. The vertical distance through which the object falls is H. Initial velocity, this will be in the vertical. This is s in the vertical. This is y in the vertical, acceleration in the vertical. So this part will be 0 because the initial velocity in the vertical is 0. So this will be equal to a half. Acceleration in the vertical is g, and then times the time t squared. So we can easily show that h is equal to a half times gt squared in the vertical. Let us see a few examples before we advance. An object is projected horizontal at a speed of 15 meters per second from the top of a tall tower of height 35 meters. Calculate how long it takes to fall to the ground. So we want to find how long it takes to fall to the ground. How far? Part B, calculate how far. How far it travels horizontally. And part C, its speed just before it hits the ground. Okay. So I will not, if you want, you can always sketch this. Of course, in an exam, normally the examiner tends to sketch the diagram for the student to simplify the student's life. But of course, even if it is not sketched, this is a very easy, it's relatively easy, I can say, but I can still sketch this for you. So let's say an object is projected from the top of a tower. Let this be the tower. And the object is projected horizontally initially with an initial speed of 15 meters per second. And the tower is at a height of 30 meters. So it is 35 meters. From the top of a tall tower of height 35 meters, calculate how long it takes to fall to the ground. So let's say this is the ground. Of course, the path followed by this is going to be of that nature. Okay, so let me change the color here. So let's find how long it takes to fall to the ground. That is now time. Do not forget the Suvart equations. V equals to U plus AT. V squared equals to U squared plus 2AS. And S equals to UT plus a half AT squared. And I think the last equation is going to be the most important equation here. So how long it takes to fall to the ground? Remember, time is a scalar quantity. Whether you consider horizontal motion or vertical motion, the time is going to be the same thing because time is actually a scalar quantity. The time in the horizontal is the same as the time in the vertical. So we have the vertical distance, we have the horizontal distance, but remember, initial velocity in the vertical is equal to 0 because the body was projected horizontally. So I can use, I could use in part A, I could use S equals to UT plus a half AT squared. S is going to be 35 because initial direction of motion is downward, so it is 35 positive. Initial velocity in the vertical is 0 because the body was projected horizontally, so this will be 0 plus a half times acceleration is going to be 9.81 times t squared. So I'm considering s in the vertical, initial velocity in the vertical, acceleration in the vertical. S in the vertical is h, which is 35. Initial velocity in the vertical is 0. Acceleration in the vertical is 9.81 and it is positive because the body did not move above the point of projection. It just moved downwards. So acceleration in the vertical remains positive. So this will give me the value of t. I'll just press my calculator. This will be 35 times 2 divided by 9.81 under the square root. 35 times 2 divided by 9.81 under the square root. So the value of t is 2.7. So that is the time it takes to hit or to reach the ground, 2.7 seconds. You can also verify. Maybe I've made an error, but I don't think so. Then how far it travels horizontally. So we want the horizontal distance here. Call that x. So by all means, I must consider motion in the horizontal, but remember the time is the same. So using s, this time in the horizontal is going to be initial velocity in the horizontal times t. For time, I will not put x or y because t is a scalar quantity, so plus a half acceleration in the horizontal times t squared. However, I want you to remember that acceleration in the horizontal is 0 because there is no force acting in the horizontal, because the speed in the horizontal remains constant. So s in the horizontal is what I want to find. I'll quote x equals the initial velocity in the horizontal, which is 15, then times time. Of course, time is the same, 2.7. Then plus this part here becomes 0 because acceleration in the horizontal is 0, so that is plus 0. So it means the displacement or the horizontal distance is going to be 15 times, which gives us approximately 40.1. Let me see, 15 times 2.7, 40.5 meters. So this will be 40.5 meters. Then a part C, its speed just before it hits the ground. So at the point where it hits the ground, the speed has two components. It has a component in the horizontal, which we shall call Vx. It has a component in the vertical, which I'll call Vy. Then the resultant of these two is the resultant velocity with which it hits this point. So this is going to be the resultant. I'll call it V. And I said we shall find that V using Pythagoras theorem. So V is going to be equal to the square root of Vx squared plus Vy squared, because it hits the ground at this point when it has both the horizontal velocity and the vertical velocity. The horizontal velocity remains the same. It remains 15 meters per second because velocity in the horizontal does not change. The vertical velocity is the one which changes and can be given by Vy equals to Uy plus acceleration in the vertical times t. I'm using the first equation. So initial velocity in the vertical is 0 plus 9.81. The time remains the same, 2.7. So Vy is going to be 9.81 times 2.7. So this gives us 26.5 meters per second approximate to three significant figures. So it means the resultant velocity is going to be the square root of Vx, which is 15 squared, plus Vy, which is 26.5 squared. So I'll just say 15 squared plus 26.5 squared, root of the answer. So V is going to be equal to 30 point, about 30.5 meters per second. So that will be the velocity with which it hits the ground. So just see how I manipulated or how I played with this question until the end of up to the end. So you should also be able to do the same thing. Let's see if there is another example. Example number 2, a stone is thrown horizontally with a velocity of 12 meters per second from the top of a vertical cliff. Calculate how long the stone takes to reach the ground, 40 meters below, and how far the stone lands from the base of the cliff. Okay, so I can sketch this for simplicity. So let this be the cliff, and it is projected horizontally with a velocity of 12 meters per second. Let this be the base of the cliff, and of course it's going to move in that path, in that kind of path. So this is 40 meters above the ground. So we want to calculate how long the stone will take to reach the ground and how far. So how far from the cliff, from the bottom of the cliff, we shall get this distance here, call it x. Okay, so it's almost the same question we have solved. So for part A is how long, which is time. So for part A, I will use S equals to U plus UT plus AT half AT squared. And remember, we consider vertical and horizontal motion independent. So I'll say S in the vertical equals to the initial velocity in the vertical times acceleration in the vertical. Remember, S in the vertical is 40 meters. Initial velocity in the vertical is 0 because the body was projected horizontally. Acceleration in the vertical is going to be 9.81 meters per second squared. So I'll just substitute to find t. So s in the vertical is 40. It is not negative 40 because initial motion was not above. It was just downwards. So 40 is going to be equal to 0 plus a half times 9.81 times t squared. So t is going to be equal to the square root of 2 times 40 divided by 9.81. So I'll say 80 divided by 9.81 root of the answer. So I'm finding the value of t as approximately 2 point. Let me write three significant figures and I say 86 seconds. Then calculate and how far the stone lands from the base. So I want to find x. How far the stone lands from the base, that is x. I'll call that one b. So using the same equation s, but this time in the horizontal because how far it lands, that is in the horizontal. S in the horizontal is going to be initial velocity in the horizontal times t plus a half times acceleration in the horizontal times t squared. Remember, acceleration in the horizontal is equal to 0, which means this part will be 0. Initial velocity in the horizontal is 12, so I'll say s in the horizontal, which is just x, is going to be equal to 12 times t, which is 2.86, because time is a scalar quantity. So this is going to be 12 times 2.86. This is giving us approximately 34.3 meters. Now I will create my own third equation, that is finding the velocity with which it lands at this point here. Remember, it has velocity in the horizontal which remains 12 meters throughout. Then it has velocity in the vertical which we are going to find as Vy. Then the resultant is the resultant velocity there. So velocity in the horizontal, velocity in the vertical with which it collides or it hits the ground is initial velocity in the vertical plus acceleration in the vertical times t. So this becomes initial velocity in the vertical, remember, was 0 plus 9.81. The time is 2.86. So the velocity in the vertical with which it collides or it hits the ground is going to be 9.81 times 2.86. So this is 28.06 meters per second. So the resultant velocity with which it hits the ground is going to be the square root of 12 squared plus 28.06 squared, which gives us 12 squared plus 28.06 squared. Then root of the answer. So this is 30.5 meters per second. That is the velocity with which it hits that point, the ground. A particle is projected horizontally at 20 meters per second from a point 78.4 meters above a horizontal surface. Find the time taken for the particle to reach the surface and the horizontal distance traveled in that time. So you can try out this. I'm just going to sketch for a diagram and I will just press my calculator to give the answer without showing any working. So let this be the top. It is projected horizontally with a speed of 20 meters per second and it follows, say, that path. Then it is at a distance of 78.4 meters above the horizontal. So we also want to find the horizontal distance, this distance in the horizontal, which I'm going to call x. So find the time taken. So I'll just find the time. I'll just press my calculator to find t. So h is 78.4 times 2 divided by 9.81 square root of the answer. So I expect that when you calculate this, you get the time as approximately 3.998 or approximately 4.0 seconds. Then x in the horizontal, I expect your value of x to be just 20 times 4. It should be 80 meters. Show the working, write the formula. Then the velocity with which it hits this point here, the velocity with which it hits the ground is going to be, let me see, 9.81 times 4 squared plus 20 squared to the answer. I think that is going to be approximately 44 meters per second. Let me check the answers again. The first one is 78.4 times 2 divided by 9.81 root of the answer. Okay. The other one is 20 times 4. Yeah, so these answers, I think they are correct. So you can check these answers if you have understood the examples that I've given. A projectile is fired horizontally from the top of a cliff 250 meters high. The projectile landed 1.414 times 10 to the power of 3 meters from the bottom of the cliff. So let me sketch this. So this is the cliff. It was projected horizontally. Its speed is not known. Then it falls. So this is a height of 250 meters. And they are saying it falls at a distance of 1.414. What is that? 1.414 times 1000. So this distance is 1414 meters from the bottom of the cliff. Find the initial speed of the projectile. Note that the speed is in the horizontal. So to find that speed, I will need to consider horizontal motion, but I will need to find the time too. Yet the time is in the vertical. The time is in the the time can easily be found in the vertical. So if I consider vertical motion and I use s in the vertical equals the initial velocity in the vertical times t plus a half acceleration in the vertical times t squared. S in the vertical is 250. Initial velocity in the vertical is 0 because the projectile was horizontal. So this is a half times 9.81 then times t squared. So I can find the time for the journey. The time is going to be 2 times 250 divided by 9.81 under the square root. So finding the square root here, 2 times 250 divided by 9.81, the time is 7.14 seconds. That is the time for flight. So if I want to find the initial velocity in the horizontal, because it was projected horizontal, I have to consider horizontal motion. And I use s in the horizontal equals the initial velocity in the horizontal times t plus a half acceleration in the horizontal times t squared. Remember, the acceleration in the horizontal is 0. So this part becomes 0. So s in the horizontal is given as 1414. Initial velocity in the horizontal is not known, but the time is the same, which is 7.14. So initial velocity in the horizontal is going to be 1414 divided by 7.14. 1414 divided by 7.14. So initial velocity in the horizontal is going to be 198 meters per second. Okay, then I'll find the velocity of the projectile just before it hits the ground. So remember the velocity in the horizontal remains the same. So velocity here in the horizontal remains 198. It's the velocity in the vertical which changes. Let me change the color here. So at the point of hitting the ground, it has velocity in the horizontal, it has velocity in the vertical, and the resultant is the velocity with which it hits. So velocity in the vertical is the one I want to find. Now this is Roman 2. From initial velocity in the vertical plus acceleration in the vertical times t, which is 0 plus 9.81 times t, which is 7.14. So 9.81 times 7.14, this is going to be 70.04 meters per second. Then it means the resultant velocity is the square root of velocity in the horizontal squared plus velocity in the vertical squared, which will be the square root of 198 squared plus 70.04 squared. So 70.04 squared plus 198 squared under square root. So this is 210 meters per second. You can also verify. Okay, so I think that is enough for horizontal velocity or horizontal projection. Let's now concentrate on projection at an angle which is not in the horizontal, because horizontal projection is always very easy. Let's now consider projection at an angle, such as demonstrated in these animations. Suppose the body is projected at an angle which is not in the horizontal, but at an angle maybe between 0 and say 90 degrees. How do we handle such projectile motion? Okay, so we are going to consider a body projected with a speed, say u, at an angle. Of course, one of the applications we mentioned about projectiles, we said if throwing a ball, for example. These animations are demonstrating what we really understand by projectiles. So let me just talk about the first animation here. When a body is projected through, say, this path here, and it moves, we notice that the velocity in the horizontal is always going to remain constant in the horizontal. The arrow in the horizontal is not changing in length, but the velocity in the vertical is going to be decreasing because the acceleration is acting vertically downwards. At the highest point here, I want you to notice that the velocity at the highest point here in the vertical is going to be 0. Velocity in the vertical becomes 0 at the highest point, but the velocity in the horizontal is always going to remain Vx. That means even though the velocity in the vertical becomes 0, the body still has kinetic energy because there's a velocity in the horizontal. At maximum height, velocity becomes 0 in the vertical, but the velocity in the horizontal is always remaining. That's why you see the arrow in the horizontal is not changing. There is always an arrow in the horizontal because there is always velocity in the horizontal. So I also want you to notice if a body is projected at an angle, like as shown in the second animation here at the bottom, at an angle, say theta. In the vertical, we have displacement. For example, displacement against distance in the horizontal. So in the vertical, you notice that if it leaves one point and comes back to the same level, displacement upwards could be positive, displacement downwards could be negative. So if it comes back to the same level, it means that the displacement in the vertical is 0. But the displacement in the horizontal is going to be this distance here, because in the horizontal there was no change in direction. But in the vertical, the body first went up and then it came down. So let's say it goes up positive and then it comes down negative. Displacement in the vertical becomes 0, but displacement in the horizontal will be 250 meters, as we are going to see. Okay. So for projectile motion, therefore, we are saying that in this kind of motion, a body is going to move in two dimensions. And what is very important for us to notice on this motion is that the velocity in the vertical goes on changing, but the velocity in the horizontal remains constant. It remains constant in that case. So the velocity in the vertical goes on decreasing, but the velocity in the horizontal is going to remain constant. And then when we reach the highest point, if we reach the highest point here, we have said that in the highest point, at the highest point, velocity in the vertical goes to zero. So that means the resultant velocity at the highest point is only velocity in the horizontal. And as the body now starts falling down, we notice that the velocity in the vertical has changed direction this time, but it is also growing in magnitude. And if you observe, the length of the line at this point here in the vertical is the same as the length of the line at this point in the vertical, simply because they are ending at the same level. So if they end at the same level, remember when it is going upwards, the velocity was decreasing at a rate of 9.81 meters per second every second in the vertical. That means even when it is falling downwards, the velocity will be now doing the opposite, that is increasing at a rate of 9.81 meters per second every second. So going upwards, velocity in the vertical decreases. Coming back downwards, the velocity in the vertical increases. But the resultant velocity at this point here is going to be the same as the velocity with which it is projected at this point. But I don't want you to forget the projection is at an angle. So if air resistance is not negligible, the horizontal component of velocity decreases if air resistance is not negligible, and the vertical component increases to a constant value, sometimes called terminal velocity. That is, if the object is falling. If there is air resistance in the horizontal, it means the velocity in the horizontal is in this direction, the air resistance will be in the opposite direction. So in that case, velocity in the horizontal would decrease. But if there is no air resistance, it remains constant. If there is air resistance in the vertical, remember air resistance acts in the opposite direction to motion. So if there is air resistance still in the vertical, velocity decreases when the body is going upwards, and it will decrease when it is going downwards, because in both cases air resistance reduces the resultant force, and in both cases air resistance acts in the opposite direction to motion, so it will certainly change in both cases. So this is what I've been just talking about for simplicity. So the vertical velocity decreases on the way upwards. So the red arrow is showing velocity in the vertical, and we are noticing that the red arrow is becoming smaller. Of course, at the highest point here, there is no vertical velocity because it becomes zero. The vertical velocity now increases on the way down. That's why we notice that the arrows are showing that going downwards, the vertical velocity is increasing, the arrows increase, but there has been a change in direction, which means there's also been a change in displacement. Initially, going upwards, the arrows are pointing upwards, and going downwards, the arrows are pointing downwards. At the highest point, or at the top of the trajectory, or at the top of the journey, the velocity in the vertical, we saw it was zero. But look at the blue arrows, which are showing the velocity in the horizontal. They have remained the same length throughout the motion, which means that the velocity in the horizontal remains the same throughout the motion. The velocity in the horizontal remains the same throughout the motion. So components, if it is horizontal, it remains constant throughout, and the direction also remains constant. For vertical velocity, it decreases when we are going upwards, it is zero at the top, and it increases when we are going downwards. The direction has changed for velocity in the vertical. So velocity in the horizontal does not change direction, velocity in the vertical does change direction. velocity in the vertical decreases to 0, then it becomes 0 at the top, then it increases as we move downwards. Okay, I hope I've tried my level best to emphasize what is really happening. So what happens when an object is thrown at any angle with the horizontal? So we want to find we want now to find what we are going to call the components. Remember, I told you that your concepts of resolving should become part of you. Let's consider an object projected at a velocity, say v, with a velocity v at any angle theta to the horizontal. So the velocity v has two components. One component must be acting in the horizontal and one component must be acting in the vertical. So if I bring this one here, it will be something like this in the vertical. So this will be velocity in the vertical, or initial velocity in the vertical, and this will be initial velocity in the horizontal. So I come up with a triangle. So the v is going to be the resultant of these two because they will be at right angles. So I will come up um, with this right angle triangle after joining them. The horizontal component, I'll write it as v subscript o, which is going to be original velocity or initial velocity in the horizontal and initial velocity in the vertical. And of course, you'll notice that v naught can be v naught x squared plus v naught y squared. However, if I resolve v naught to the horizontal using v naught x to the horizontal, this is adjacent hypotenuse, that is cos. So I have that cos of theta is going to be equal to v naught in the horizontal divided by v naught. So it means the component of v naught in the horizontal is going to be v naught cos of theta. If I consider the opposite and the hypotenuse, that will be sine, and I'll have that sine of theta is equal to v naught in the vertical divided by v naught. So v naught in the vertical is going to be equal to v naught sine of theta. So this will be the horizontal component of the initial velocity, and this will be the vertical component of the initial velocity. So if motion is in more than two dimensions, that is both in the vertical and the horizontal, we shall need both the horizontal and the vertical components every time. So we shall always need to resolve this. So the horizontal motion, the initial velocity in the horizontal is going to be v naught cos v naught x equaling to v naught cos of theta. And then in the vertical, we have initial velocity as v naught y being equal to v naught sine theta. Note that in the vertical, in the horizontal, the acceleration is 0, and in the vertical, the acceleration is negative g, which is going to be negative 9.81. So this is going to be very, very important when we are dealing with calculations for that matter. It will be very important. So at every instant, therefore, we shall be able to use the trigonometric ratios. So a few things we need to note from here. All the vertical components will have a subscript y. For example, Vy, Sy, and so on and so forth. And all the horizontal components, I'll always put there a subscript x for convenience. When you become an expert, you don't need to mind about subscript x or subscript y. For example, when I say Vx, that is velocity in the x. Sx, that is displacement in the x. If the object begins and ends at the same level, like in this illustration here, it means the displacement is 0. That means s in the vertical is 0. Of course, s in the horizontal can't be 0 in this case because the displacement in the horizontal has not changed. If it starts from here, goes up, positive h, comes down, negative h, total displacement in the vertical will be 0. And I want you to notice that the velocity in the vertical goes on decreasing and is 0 at the highest point, but in the horizontal it is not 0. That means even though the velocity in the vertical is 0, the kinetic energy of a body can never be 0 if it is a projectile, simply because there will always be velocity in the horizontal which is never going to be 0 for such a motion. There will always be some velocity in the horizontal, so the kinetic energy can never be 0. What is very important here is to learn to resolve. And at every point, the velocity has two vectors, apart from the highest point where the vertical component is 0. But you can notice that from these vector diagrams at all points, this is the resultant at all points. And when you look at the arrow at the bottom here, it is the same length as the arrow here. So that means the velocity here is the same as the velocity here, only that the two are in opposite directions. Why is it the same in magnitudes? Because the object has reached the same level. The velocity here is the same as the velocity here if these two are the same level, only that these will be in opposite directions. And that is going to be very important. Okay, let's use this in calculations. Therefore, having got the basics about projectile motion, it will be easier to understand them if we use them in calculations. But I want you to note that if air resistance is not negligible, the horizontal component and the vertical components will all change. The horizontal component of velocity will decrease because when the body moves to the right, the air resistance moves in the opposite direction. And the vertical component of velocity, it would increase at a constant and then reaches a constant value which remains, which we call terminal velocity, depending on the direction of motion of the object, as we saw in dynamics. And I'm saying you should also be able to resolve to get the components of velocity. Example number 1. A projectile is fired from the ground level with a velocity of 700 meters per second this is supposed to be at, I think, at 38 degrees to the horizontal. Find the horizontal range, that is going to be the horizontal distance, the greatest height to which it rises, the time taken to reach the greatest height. So, of course, in the exams, the diagram is normally sketched. For now, I will sketch for you the diagram. So the projectile is like this at an angle. So it is projected with a speed of 700 meters per second at an angle of 38 degrees to the horizontal. So we want to find the horizontal range. I'll call this one X or R. Then we want the greatest height. This is the greatest height. I'll call it capital H. Then the time to reach the greatest height. So Roman 1, the horizontal range. For horizontal range, I must consider horizontal motion. So using S in the horizontal equals to the initial velocity in the horizontal times t plus a half acceleration in the horizontal times t squared. Remember, the acceleration in the horizontal is 0 because there is no force in the horizontal if air resistance is negligible. So it means the horizontal distance is the range. Initial velocity in the horizontal is 700 meters per second then times t, which t we don't know. However, if I consider vertical motion, S in the vertical equals to initial velocity in the vertical times t plus a half. Oh, by the way, this was 700, so I have to resolve this horizontally. This is not going to be true. The velocity in the horizontal, sorry about this. The velocity in the horizontal is going to be 700 cos of 38. The velocity in the vertical is going to be 700 sine of 38. So this is going to be 700 cos of 38 times t. Then considering vertical motion, S in the vertical is u in the vertical times t plus a half, acceleration in the vertical times t squared. So considering vertical motion, S in the vertical is going to be 0 because the body leaves the point of projection and comes back to the same level. So S in the vertical is going to be 0. Going upwards, a distance h. Coming downwards, a distance h. Displacement is 0. So 0 is going to be equal to initial velocity in the vertical, which will be 700 sine of 38, then times t, then minus, because the acceleration in the vertical is going to be negative 9.81 because the body moved against gravity initially. So it is negative 9.81 meters per second squared. So minus a half times 9.81, then times t squared. So solving for t is going to be equal to 1 t cancels out. So I will say 2 times 700 sine of 38 divided by 9.81. So the value of t is going to be 2 times 700 sine of 38 divided by 9.81. So t is going to be 87.86 seconds, or approximately I can say 88 seconds. That is t. That is the time to leave the point of projection until it lands. So that means now I can find the horizontal range as 700 cos of 38 times 88. So this is giving me 48,541, or approximately 48,500 meters as the horizontal range. So I have found the horizontal range. Then Roman 2, the greatest height. So to find the greatest height in Roman 2, I will consider vertical motion, and I will say, remember the highest point v is 0. At the highest point here, velocity in the vertical is 0. So I will say v is equal to u plus at, but this one has no h, so I'll use v squared equals to u squared plus 2as. V squared equals to u squared plus 2as, where s is the highest value, the highest height. So 0 squared in the vertical, remember I'm considering vertical motion. 0 squared equals to initial velocity in the vertical, which is 700 sine of 38, but this should be squared, minus, because the acceleration is going to be negative in the vertical. So 2 times 9.81, then times h. So this becomes 700 sine of 38 squared divided by 2 times 9.81. So I've just made h the subject, and I said h is going to be equal to 700 sine of 38 squared divided by 2 times 9.81, and here the answer is 9466, or approximately 9500 meters. So that will be the greatest height. Then the time taken to reach the greatest height. Of course, I could get this time and divide it by 2, or I could use v equals u plus at in the vertical. So I don't have space here. Let me use this space. This is going to be Roman 3. So v in the vertical is equal to initial velocity in the vertical plus acceleration in the vertical times t, where t is the time to reach the highest point. But at the highest point, v is 0. So I will say 0 equals the initial velocity in the vertical, which is 700 sine of 38 plus, but this becomes negative because it's moving against gravity. So it's minus 9.81, then times t. So I'll just make t the subject by dividing. So t is going to be 700 sine of 38 divided by 9.81. I expect this to be around 44. 700 sine of 38 divide by 9.81. So this is approximately 44 or 43.9 or approximately 44 seconds, which is just a half of this. Because the time to reach the highest point is half the time for the whole journey. Okay. A ball is thrown with an initial velocity. The ball is thrown with an initial velocity of 20 meters per second at an angle of 30 degrees to the horizontal as shown. Like I said, normally in the examiner will give you a diagram for the question. The examiner normally gives you a diagram for this question. Calculate the horizontal distance traveled by the ball. That is going to be called its range. So we want the horizontal distance. Initial velocity in the is 20. So our velocity in the horizontal. In the horizontal, we have 20 cos of 30. In the vertical, we have 20 sine of 30. So we have the values of velocity in the horizontal and in the vertical. We want to find the horizontal distance traveled by the ball from here up to that point. So to find the horizontal distance, I must consider horizontal motion. So considering horizontal motion or motion in the horizontal, S in the horizontal is equal to initial velocity in the horizontal times t plus a half acceleration in the horizontal times t squared. But remember, acceleration in the horizontal is 0. So S in the horizontal, which is going to be the range, let me call it just X. So X is going to be equal to 20 cos of 30 times the time t, but I don't have t. However, I can consider vertical motion to find t. Vertical motion. S in the vertical equals to initial velocity in the vertical times t plus a half acceleration in the vertical times t squared. S in the vertical is 0 because the body falls at the same level as the point of projection. So the displacement in the vertical, upwards is positive, downwards it is negative, and the same magnitude they cancel out. So 0 is going to be equal to 20 sine of 30, then times t, minus, because the acceleration is going to be negative 9.81 in the vertical since the body moves above the point of projection. So this will be minus 9.81 over 2 times t squared. So 1 t cancels. So you get t as 2 times 20 sine of 30 divided by 9.81. So you just press your calculator, 40 sine of 30 divided by 9.81. So t is equal to 2.04 seconds. So it means the horizontal distance we are talking about here, x, is going to be equal to 20 cos of 30 times t, which is 20 cos of 30 times 2.04, which is going to give us 2.04 times 20 cos of 30. So this is giving me 35 meters, approximately 35 meters or 35.3 meters. Okay. The bullet is fired from a gun placed at a height of 200 meters with a velocity of 150 meters per second at an angle of 30 degrees. Find the maximum height attained. So a bullet is fired from a gun placed at a height. So the gun is already at a height of 200 meters. So I may try to sketch this maybe for simplicity. Let me try to sketch this. Let's say this is the height above which the bullet is fired. Let's say this is the ground. So the bullet is fired at that height, but again it is fired at an angle with a speed of 150 meters per second. So it is going to move at an angle and then it falls to the ground. So this angle is given as being 30 degrees. I said in the exam, normally the examiner gives you the diagram in most cases. So that is going to be, I think, the diagram. The vertical distance, the vertical height here was 200 meters. So find the maximum height attained. In other words, we want to find this height, which is going to be 200 plus small h. So this height is 200 plus h. So this only height here, let it be h. Okay. Then the time taken for the bullet to hit the ground. So we want the time it takes for it to hit here. So to begin with, I'm going to find a small h using maybe I can consider vertical motion. If I consider vertical motion for Roman 1, and I will use, remember at the maximum height here, v in the vertical is equal to 0. So using v squared equals to u squared plus 2as. I'm now going to consider vertical motion because okay, I'm going to find the vertical height h first. Oh, I'm finding the maximum height h. So at the highest point v is 0, so I'll say 0 squared equals to initial velocity in the vertical. So I have to resolve velocity in the vertical. So let me change the color here for simplicity. So in the horizontal it is 150 cos of 30. In the vertical, when I resolve, it will be 150 sine of 30. So this will be equal to 150 sine of 30, but this should be squared, minus, because it initially moved against gravity, so the acceleration in the vertical is going to be negative 9.81. So this will be minus 2 times 9.81, then times the small h. So small h is going to be equal to 150 sine of 30, but this should be squared, divided by 2 times 9.81. So small h is going to be equal to, I'll press my calculator, 150 times, so this is giving me 287 meters. So it means the maximum height we said it is 200 plus small h, which is going to be 200 plus 287, and this becomes 487 meters. Okay. Then the time for the bullet to hit the ground. Time for the bullet to hit the ground. Okay. So there are two ways of doing this. One, you could consider the whole journey. When it moves upwards, a distance of positive small h. Then it moves downwards, a distance of negative h. So it means positive h and negative h cancels out if it was to stop at the same level. But it continues in the negative direction, a distance of 200 meters. So that means the displacement is negative 200 meters. So in Roman 2, I'll first consider that condition, and I'll say s in the vertical equals to the initial velocity in the vertical times t plus a half, acceleration in the vertical times t squared. And I said the displacement, therefore, if it continues below the point of projection, it will move a further distance of 200 in the negative direction downwards. So the displacement is going to be negative 200, which will be equal to initial velocity in the vertical still. it was 150 sine of 30, then times time, which I'll just call capital T, minus a half. G in the vertical is 9.81, then times T squared. So if you're good at mathematics, if you're a mathematician, you should be able to solve this. I'll just rearrange it for you. You could use a calculator to solve this quadratic equation. I'm just rearranging the equation for you. So it becomes, when I take everything to the left-hand side, I'll have 9.81 t squared uh, minus 150 times 2, 150 sine of 30 is, I think, 75 times 2. Everything is multiplied by 2, so it becomes minus 150 t. Then 200 by 2, it becomes minus 400. And this is equal to 0. So you can solve that and find your value for t using any equation you want. Or if you have a scientific calculator, just put the equation in the calculator. I think mine can also solve that. Let me put it in the calculator. Or you can use the general quadratic equation to find t. My calculator is giving me t as 17.6 seconds. But that may not be easy for a non-PCB, math student. I'll give another alternative. Alternative 1, I'll find time to maximum, to the highest point. I'll first find time to the highest point. Time to the highest point, I'll call that one T1. And I'll get it from V equals to U plus AT. Remember, V is going to be in the vertical, U in the vertical, acceleration in the vertical. At the highest point, V is 0. So I'll say 0 equals to 150 sine of 30 minus 9.81 times t. So this means the time t1 is going to be equal to 150 sine 30 is 75 divided by 9.81. So the time to reach the highest point is going to be 7.65 seconds. Then I'm going to now consider motion starting from the highest point. Consider motion independent starting from the highest point. So from the highest point downwards. So it means initial velocity in the vertical this time is going to be 0 if we start from the highest point where velocity is 0 in the vertical. So from the highest point, initial velocity is going to be 0. So if it is going to be 0, then I'm going to use S equals to UT plus a half AT squared. To find now the new time, I'm going to call this one T2. So S, it follows a distance which we have calculated as 487 in the vertical. So it will fall through 487 equals to, remember it started from the highest point, so this part becomes 0, so this will be 0 equals to a half. Now when I consider the starting from the highest point, it means acceleration will now be positive because I'm considering motion downwards independently. So this will be 9.81 meters per second squared. So this will be times 9.81, then times t, which I will call t2 squared. So what is t2 then? So this implies that t2 is going to be equal to, I've just pressed my calculator, 2 times 487 divided by 9.81, then find the square root of the answer. This is approximately 9.96 seconds. So I now find the total time, which I'll call t, which is the sum of these two. 7.65 plus 9.96. So 9.96 plus 7.65. So this is going to be 17.61, or approximately 17.6 seconds. So you can find the time to reach the highest point and the time from the highest point to the ground, and then you sum up to get the total time. So that would be the total time. Of course, remember you can find the velocity the way we found it from our horizontal projection. Remember the velocity in the horizontal always remains constant. Then the velocity in the vertical increases. Then you use Pythagoras theorem to find the resultant velocity. A shot is fired of from the top of a cliff 200 meters high with a velocity of 500 meters per second at an elevation of 30 degrees. Find the time taken and the distance from the point where the shot strikes the ground to the bottom of the cliff. And then part B, this is I think part B, the distance from the ground to the highest point. Okay, so let me try to sketch the diagram somewhere here. So this angle is going to be 30 degrees to the horizontal. This is given as 200 meters. They want us to find the distance here, which I'll call x. This is given as 500 meters per second. So the time taken and the distance from the point where the shot strikes the ground to the bottom of the cliff, that is x. Then the distance from the ground to the highest point reached, that is capital H. We need to find this distance here, which will be 200 plus h. Okay, so we want the time and the distance from the point where the shot strikes the ground to the bottom of the cliff. In other words, we want to find the total time for the whole flight, and we want to find total distance. So since I said you can find, we have done a similar example in the previous part. When the example 3 is exactly the same as this one, so I'll just do this from my calculator and give the values. So for the time of flight, I'm going to consider vertical motion. Displacement is going to be negative 200. So displacement is negative 200 in the vertical. Displacement in the vertical is equal to negative 200 using s equals ut plus a half at squared. I'm just going to put this in a quadratic equation. So from my calculator, I'm finding total time for the whole journey as being equal to 51.76 seconds. Do not forget to resolve velocity in the horizontal and velocity in the vertical as we got in example 3. You should be able to do this if you are really following these lessons. Alternatively, I said you can find the time to reach the highest point, and then you find the time to fall from the highest point to the ground. But remember, I said you have to consider that time from the highest point to the ground independently as independent motion. And if you consider it as independent motion, you consider it as if it is falling from rest, then falling downwards, where g will now be positive rather than negative. Then you sum up the time. Then so the time is that. Then the distance, I'll check the distance. Of course, the distance from the point where the shot strikes the ground to the bottom of the cliff, that is the horizontal distance. I've called it x. I'll just check with my calculator. Okay, so following from example 3, you should be able to get a distance of approximately 22,400 meters to three significant figures approximately. So this is Roman 1, Roman 2. Then Roman 3, Roman 3 is the vertical distance. For Roman 2, I used S in the horizontal equals to initial velocity in the horizontal times t plus a half, acceleration in the horizontal times t squared, but putting in mind that acceleration in the horizontal is equal to 0. So it means this part becomes 0. Remember, initial velocity in the horizontal, you have to resolve 500 in the horizontal. If you want in the vertical, you have to resolve 500 in the vertical. Like when I was finding t, I had to resolve 500 in the vertical. Initial velocity in the vertical is 500 sine of 30. Then for Roman 3, I'm going to use v squared equals to u squared plus 2as. At maximum height, v is 0. I'm finding small letter h. So small letter h is going to be equal to, I will not show you the working, I've done it in example 3. I've just put in my calculator. So small h is going to be 3,200 meters to two significant figures. And I expect to find the maximum total distance to be 200 plus 3,200, which should be 3,400 meters approximately. So try to follow from example 3 and see if you will get the same answers that I've got in example 4. Example 5, a particle is projected. The particle is projected at 20 degrees to the horizontal and just clears a wall 10 meters high and 30 meters away from the point of projection. Find the speed of projection, velocity of the projectile. Find the speed of projection, velocity of the projectile when it strikes the building. Okay, I think I will solve this. Find the speed of projection and the velocity of the projectile when it strikes the building. So when it strikes the building and the time taken to reach the building. Okay, so I'll have to sketch this first. So let's say this is the initial position and this projector is going to be projected so that it strikes. Let's say it strikes the building at this point. Let's say this is the building and the building is at a distance of 30 meters from the point of projection. The projector is at a speed which is not known. Let me just call it u, but is at an angle of 20 degrees. And it just clears a wall 20 meters high. So the wall is 10 meters high away from the point of projection. So we want to find the speed of projection, that is going to be u, and then the velocity with which it clears or it strikes the building, that is going to be the velocity here. Of course, at this point, the velocity has two components. I'll change the color for simplicity. It has a component in the horizontal and a component in the vertical. Then we are looking for the resultant at that point, which is going to be Vy and Vx squared, Vy squared plus Vx squared under the square root. Okay, so let's start with for the initial velocity. So for the initial velocity, we are going to consider horizontal motion to find the initial velocity. So using S in the horizontal equals to the initial velocity in the horizontal times t plus a half times acceleration in the horizontal, then times t squared. Remember, the acceleration in the horizontal is equal to 0. But in the horizontal, sx, s in the horizontal is equal to 30 meters. So I will substitute. So I'll say that 30 equals to, we have to resolve 20 in the horizontal. I mean, u in the horizontal will be u cos of 30. That is initial velocity in the horizontal. Then times the time it takes, so which I'll just call it t. This other part will become 0. That part becomes 0. So I can simply say, or I can authoritatively say, that the time t is going to be 30 divided by u cos of 30. That's number one. Then I'm going to also consider vertical motion. Vertical motion. And I'm going to use the same equation. S in the vertical this time is going to be initial velocity in the vertical times t plus a half acceleration in the vertical times t squared. S in the vertical, at the point when it strikes the wall, S in the vertical is 10, I think. Yes, 10. Initial velocity in the vertical will resolve u to the vertical, which will be u sine of 30. Of course, time is the same, it is a scalar quantity. Then plus, so this will become, of course, the acceleration in the vertical is going to be negative 9.81. So this will be minus 9.81 t squared divided by 2. So when I solve this, or when I simplify this out, okay, this one gives me u without even hesitation. This one is giving me u without even hesitation, because note that t is 30 divided by u cos of 30. So if t is 30 divided by u cos of 30, sorry, not cos. Where did I get cos 30? This is cos of 20. So I'm going to substitute. I'll get 10 equals to u sine of 20 times 30 divided by u cos of 20 minus 9.81 over 2 into 30 divided by u cos of 20, but this is squared. So the u here cancels out. I'm going to press my calculator to try and simplify this. So 10 is on one side. I'll first take a one quantity on one side, multiplying everything by 2. I have 20. 20 is equal to 60 sine of 20 divided by cos of 20 minus 9.81 into 30 squared over, okay, into 30 divided by u cos of 20. Of course, this is tan. So I just want to take one quant on one side, so I'll have 9.81 into 30 divided by u cos of 20, but this is squared, being equal to 60 tan of 20 minus 20. So I'll just simplify now from this point. From using my calculator, I've done a lot of algebra, which is not necessary. So I'll say 60 tan of 20 minus 20. Then I'll say divide by 9.81. Then I'll find the square root. Remember I'm making u cos theta the subject, so divide by So I'm finding the square root of the answer. So I've already removed the root. So I have that 30 divided by u cos of 20 is equal to 0.433 approximately. So I'm just going to cross multiply and make u the subject. So I have 30 divided by 0.433 cos of 20. So I'm getting 73.73. So I'm finding that u is 73.7 meters per second. You can solve that equation and see what you get. So u is 73.7 meters per second. And our task is now to find, so that is the initial velocity of projection. We want now to find the velocity at the point when it strikes the wall. That velocity has two components that we are going to find. Of course, v in the x remains the same. V in the x is still going to be 73.7 cos of 20, which is going to be equal to, so 73.7 cos of 20. So this is approximately 69.3. Then V in the y, of course, V in the y keeps changing. Is going to be initial velocity in the y plus acceleration in the y times t. Initial velocity in the y is 73.7 sine of 20, then minus 9.81 times t, which value of t is 30 divided by 73.7 cos of 20. So this is 30 divided by 73.7 cos of 20. So t is 0.43. T is 0.433. That is t. So I'm going to just substitute for t in that equation. So this is going to be 73.7 sine of 20 minus 9.81 times t, which is 0.433. So this is 20 point, it's approximately 21. Or I can say 20.96 meters per second. So this was meters per second. So this is v in the y. So the resultant velocity is going to be the square root of 69.3 squared plus 20.96 squared. (69.3 squared plus 20.96 squared under the square root). So this is giving me 72.4. The resultant velocity is 72.4 meters per second. And the time taken to reach the building, of course, the time taken, we have found it as 0.433. And the resultant velocity is 72.4. Maybe we may want to find the angle at this point here. Of course, here we can use tan. If you want the angle with the horizontal, that would be tan. So if you look at the horizontal velocity and the resultant, and then the vertical. So this vertical is Vy, the horizontal is Vx, and this is the angle theta. So opposite adjacent, that is tan. So you may want that angle, and tan theta would be equal to the opposite, which is Vy, divided by the adjacent, which is Vx. So this will be equal to Vy is 20.96 and Vx was 69.3. So this could give us theta in case we are asked to find theta. So theta will be the tan inverse of that. Let me try to press my calculator. So theta would be approximately 16.9 degrees. Okay, I think I've given enough examples and I want you to try and practice and see. If you go slow by slow or slowly by slowly, we try to pick up what I'm dealing with here. Do not always forget to resolve the velocity in the horizontal. That will be cos, that is u cos of 20, and in the vertical it is u sine of 20. I think that is not very hard. So I have another example here. A cannon located at the cliff is shot as shown in the diagram. How far from the base of the cliff will the cannonball land? I think by now this should be an easy question because I've done a lot of examples. But still, I will try to solve this. How far from the base? So we want this distance here from the base. I'll call this one x. Will the cannonball land? So one, I can find the time for the whole journey. Because remember, if I consider horizontal motion, s in the horizontal is going to be initial velocity in the horizontal times t plus a half acceleration in the horizontal times t squared. But remember, acceleration in the horizontal is 0. So in the horizontal, Sx is capital X. Initial velocity in the horizontal will resolve 110 to the horizontal, which will be 110 cos of 55. 110 cos of 55 because still this remains horizontal. So 110 cos of 55. In the horizontal, it is 110 cos of 55. Then in the vertical, it is going to be 110 sine of 55. So this must be multiplied by t, which t we don't have, and t is the total time of flight. But if I consider horizontal motion, this was vertical motion. If I consider horizontal motion and I say s in the horizontal, I mean vertical. This was horizontal initially. This is now vertical. S in the vertical is equal to initial velocity in the vertical times t plus a half acceleration in the vertical times t squared. So s in the vertical is going to be this vertical distance because it is going to fall a further vertical distance, which is 50 plus 1.5. So this is going to be negative 51.5 equals the initial velocity in the vertical, which is 110 sine of 55 minus or times t minus a half times the acceleration, which is going to be 9.81, then times t squared. So I'm going to rearrange this equation again into a quadratic equation, which you can solve using any method or your scientific calculator. So without wasting time, rearranging will give me 9.81 t squared minus, I have to multiply 2 times 110 sine of 55 minus approximately 180 times t, then minus 51.5 times 2 minus 103 equals to 0. So I'm just going to put this in my calculator to get t, which is the time for the whole flight. Or you can use a method which we have considered for finding the time to the highest point plus considering motion from the highest point going downwards. Remember I said in that case you consider, because at the highest point v in the vertical is 0, and this will be the initial velocity when you are going downwards in the vertical. So you consider that and find the time. So I'll use this in my calculator and see if I can find the equation. I'm going to find a solution to this. Degrees 2 equation, degree is okay. Maybe let me use the other simpler one, T1 to reach the highest point. I'm going to use V equals to U plus AT. T1 to reach the highest point, remember the highest point V is 0 in the vertical, so 0 equals to 110 sine of 55 minus 9.81 times T. So T1 is equal to 110 sine of 55 110 sine of 55 divided by 9.81. So I'm using the easiest method for those who don't do math. For those who do math and have a nice calculator, just press the calculator here for T. So this would be 9.19 seconds. Then from the highest point, I'll call that one T2. I'm going to use the same formula. No, I will not use the same formula. I use S equals to UT plus a half AT squared. So we're starting from the highest point. Unfortunately, we don't have S in the vertical. So that means I have again to find S in the vertical, but that is easy. V squared is equal to U squared plus 2AS in the vertical. 0 equals to 110 sine of 55 minus 9.81 times H times 2. So I'm finding the H from here to the highest point. So H is going to be equal to 110 sine of 55 divided by 2 times 9.81. So H is equal to 4.59 meters. So it means if it starts from the highest point falling downwards, total value of H is going to be 4.59 plus 1.5 plus 550. So 4.59 plus 50 plus 1.5, that is 56.09. So 56.09 is equal to, it started from rest at the vertical, at the highest point, U is 0, equals to a half times 9.81, then times T2 squared. So what is T2? So T2 is going to be equal to times 2 divided by 9.81 square root. So T2 is going to be 3.38 seconds. So total time is going to be the sum of the two. 3.38 plus 9.19. So total time is 12.57 seconds. So that is T2. So I'll take this time to that point here to find X. So it means X is going to be equal to 110 cos of 55 times 12.757, which is equal to 11 cos 55 times 12.57. So this is 79.3. Okay, so you can press your calculator and find the value of t here, but I know it is going to be 12 point something or 12.6 seconds approximately. So that is how far. I think that should be the last question. The rest should be for you to answer. So here I gave a thought-provoking question two footballers, 150 meters apart, stand facing each other. One of them kicks a ball from the ground such that the ball takes off at a velocity 30 meters per second at 38 degrees to the horizontal. Find the speed at which the second footballer must run towards the first footballer in order to trap the ball as it touches as it touches the ground. If he starts running at the instant the ball is kicked. So you have two footballers, one is somewhere here and another one is somewhere here. I'm just giving you a hint. So one football is going to kick the ball and it is going to move. But this one must run up to the point where the ball is supposed to land so that he meets the ball. So he must run through a certain distance. So the ball is going to be kicked at a certain angle, which is 38 degrees with an initial speed of 30 meters per second. And the second footballer, this is the first, this is the second footballer. He must run so that the ball does not touch the ground when it's not yet there. So the question is, find the speed at which the second footballer must run towards the first footballer in order to trap the ball as it touches the ground. If he starts running at the instant, the ball is kicked. I have given you a hint here for you to think about. Since the second footballer starts running at the instant the ball is kicked and is supposed to run so as to trap the ball as it just falls, is going to take the same time. So the time of flight here is the same time it's going to take the other side. So it's going to take the same time as the ball, as that's taken by the ball to land. That's number one. So you know the time is going to take. So the only thing you need is to find the horizontal distance. Remember the distance between the two is 150 meters. So you just need to find the time for this. You find the distance, the horizontal distance here, and then subtract it from 150, so you get the distance here. The distance is supposed to run. Of course, the time here is going to be the same as the time here. Since this one is going to run in a straight line, then you can consider the speed as being uniform, which will be distance divided by time, and see if you arrive at this answer here. I think that should be the end of projectiles. The rest are going to be solved questions for you to try out. So you can pause the video and read through the questions and try to solve them. So try solving question number 1. Try solving question number 2. Try solving question number 3. Those are easy but good for practice. And I've also given a very long self-check for you to just gain confidence, a lot of confidence. Self-check. So you can pause the video and try to solve the questions and verify if these answers are correct. Question number 1, question number 2, question number 3, question number 4, number 5. Try question number 6 and verify if the answers are correct. Try question number 7 and see if the answer is correct. You should try question number 8 and see if this answer is correct. You may get a different answer because these questions are not solved by me, they are solved by my former students. Try question number 9. You just need to a graph paper and plot the graph. Then you should also draw a second graph of V against T. And from the graph, what can you deduce about the acceleration? Remember, the acceleration is supposed to be the gradient. And if it is a straight line, you will tell that the acceleration is uniform. If it is a horizontal line, the acceleration will be 0, and so on and so forth. Try question number 10. And you should also try question number 11 and see if the answers are correct. Try question number, this was supposed to be question number 12, and this was supposed to be 13. You can correct that. You should be able to try question number 14 and see if the answers given here are correct. And try question number 15 and see if the answers given here are correct. You can pause the video and you try to work out. So finally, I've given you general questions here just to use. Prove that the time of flight t and the horizontal range r of a projectile is given by gt squared equals twice r tan of beta. So if I was to sketch this for you, so the r is the horizontal distance and t is the time for the whole journey. Beta is given as the angle of projection. So try to see if you can show that gt squared is equal to r tan beta. Of course, that is not a physics question because that involves a lot of mathematics. If you're good at math, trigonometry, you should be able to do that. Check question 16, 17, and 18 and see if the answers are correct. Of course, for 18, what is the kinetic energy of the ball at the top of its flight? The ball is thrown from a window with initial speed of 8 meters per second at 30 degrees above the horizontal. What is the kinetic energy of the ball at the top of its flight? This is not correct. This is not correct because we have said the horizontal velocity is not zero. Even though the vertical velocity goes to zero, the horizontal velocity is not going to be zero. So you need to find the horizontal component of velocity. I would just find the horizontal component of velocity at the highest point is going to be, it is going to remain the same. So Vx is going to be 8 cos of 30. Vx is 8 cos 30. So the kinetic energy is going to be a half times the mass times Vx squared because Vy becomes 0. So I will just use that. So the kinetic energy here is going to be equal to, let me substitute and see, mass is 50 grams, which will be 50 times 10 to the power of minus 3. So that would be 50 exponent minus 3 divided by 2 times kinetic energy, which is, V, which is going to be 8 cos of 30. So this is going to be 0. V is squared. So I'll say I have to repeat this because V is squared. So 0.5 times 50 exponent minus 3 times open bracket 8 cos of 30 but squared. So this gives us kinetic energy as 1.2 joules. It is not 0. So this student was wrong. His argument was wrong. So that is 1.2 joules. So check and see if you arrive at 1.2. because I'm saying at the highest point, what is the kinetic energy of the ball at the top of its flight? So at the top of its flight, the value of velocity in the vertical goes to 0, but the value of velocity in the horizontal is still constant as it was initially. And initially it was 8 cos 30, so it remains 8 cos 30 throughout. Okay, check number 18 and see if these answers are correct. I think those should be correct. Then 19, explain the terms time of flight, that is time for one complete journey, range, that is horizontal displacement. Yeah, you can try to solve these equations. So discuss the application of projectile motion in real life. We have talked about during shooting and launching of missiles, basketball, when you are trying to shoot into the basket, kicking a ball aiming at a certain point. You have seen people missing a lot of penalties because of poor calculations of their projectiles, etc. Those are everyday experiences where projectiles are very useful. And lastly, you can try to show that the time of flight of a projectile is twice the time to attain maximum height. So if the time to attain maximum height is small t, show that the time for the whole journey is equal to twice t. That is, if a body is projected so that it moves in that direction, find that the time to reach the highest point here is twice the time for the whole journey. Show that the maximum height h is equal to that one just use v squared. V squared is equal to u squared plus 2as. Just consider the same motion where this is going to be theta and this is going to be u, the velocity of projection. Remember to resolve in the horizontal as cos and in the vertical as sine. Show that the range of projectile, that is the horizontal distance, is equal to that. Check question 24 and see if these answers are correct. And check finally question 25 to see if these answers are correct. And if you have tried to practice up to this point and you have reached this level, then I think you are good enough to go. You are good enough for kinematics. I beg to stop here. Do not forget to practice the solved past paper questions. These ones could be more exaggerated, but when they are not very tricky. But in the solved past paper questions, you'll find the less exaggerated, but which are very, very tricky. So do not forget to watch the videos of the solved past paper questions. Until next time, bye bye.